Great, thank you. Yes, as mentioned, these are Chloe's slides. She led this talk, and I will do my best to channel whatever it was that she was trying to deliver in each of these slides. As I'm sure most of you know, it's a little bit of a challenge to pick up someone else's thought process. But we can go ahead and move to the next slide. So, as a reminder from this morning, we now know a great deal about Sharon. We expect it formed from a Pluto scale collision. We see various geologic processes that have shaped the surface, including potentially cryovolcanic plains, which have been associated with refreezing of a past subsurface ocean, which we'll talk about more in later slides. The fact that Sharon may have been an ocean world makes it a really interesting target to be thinking about. And in comparison with other mid-sized ocean worlds, such as moons that we see around Saturn and potentially Uranus. And that brings us kind of to the point of this talk, which is to think about Sharon in the context of some of these other bodies, comparing and contrasting morphology, composition, interior structure, and thermal evolution. Uh, please advance the slide. In terms of geologic features, these have been discussed a bit earlier in the session, so I won't dally too long. But we do see some features that are not common on other icy bodies. Mountains in a moat, for example, which is B on this image. We see a lot of extensional tectonic features, which I think will be shown more in later slides. We see hills, we see textured terrains. Clearly, this is a world where some things happened, but some of these things are familiar and some are quite unfamiliar. Next slide. There are two geologic units. We have the Vulcan Planum area where we see potentially cryovolcanic flow deposits. So these are flatter and have more sparsely cratered areas. And we do seem to see multiple epochs of activity on Sharon with this sequence of fracturing and cryovolcanism and tectonism. So we can try to use that to pull out a bit of a time series. And as we'll see on the next slide, we see a lot of tectonic features. So this map was from Ross Byers' paper, and we see a variety of different types of features. So these systems of normal faults that are very long and have steep dips, see extensive global extensional faulting. The extension that has been mapped so far seems to correspond to about 1% of overall surface expansion. Of course, we don't know what's on the other side of Sharon to this level. Um, Again, the expansion seems to be driven by freezing of subsurface ocean. That's typically what we invoke when we see icy moons that have a lot of extensional tectonism, because as you freeze the liquid into solid, you change the volume and you can extend the surface layer. And what this suggests is that there was some amount of internal heating sufficient to melt Sharon and create a large ocean, and then some kind of shutdown process where the heat source decreased or was removed entirely. Next slide. And we can compare these systems to tectonic features on other icy bodies. And here, Chloe's put together a really nice little gallery of some of these features. And as I said, in most cases, we see a lot of evidence of extensional tectonic features. We see very little evidence of compressive features. And it's not entirely clear whether these compressive features are not seen because they didn't form, or because somehow they are obscured. On Europa, for example, there may be subtle folds and things that are not as obvious as a pronounced wrinkle ridge. But in any case, we do see a lot of evidence of extensional faults, canyons, rifts, fractures, and all of these are kind of hand-wavingly attributed to the freezing of an ocean. But it is curious that they display themselves so differently on different bodies. Some are very concentrated in canyons, like on Tethys with Ithaca Chasma. Others are widely distributed, like the wispy terrains on Dione. So a big question as we look at Sharon in the context of these other worlds is why, what controls how ocean freezing expresses itself on the surface of an icy moon. Next slide. So, in addition to ocean freezing, many icy satellites are subjected to tidal stresses, and so we think about tidal stresses when we're interpreting these features. So, the most common or the most best example of this is Europa, where we see lots and lots of fractures, and they can be tied very well to tidal stresses due to eccentricity. Um, but in these cases, we expect certain types of patterns, and you can see in this graphic in the upper panel, the gray arcs are the orientations of fractures where we would expect to see fractures at that orientation if eccentricity driven tidal stresses were controlling the formation of fractures on Sharon. And as you squint at this figure, you'll see, depending on your location, you get a different wedge. So you would expect different orientations. And if you try to find the equator and you kind of look from above the equator to below the equator, you see that those predictions are mirrored. So pretty much all eccentricity stress patterns are like this, where you get a mirrored stress pattern across the equator. And when we compare this on Sharon to the fractures that have been mapped, we don't get a very good fit. So in the bottom panel of this figure, we have all of those mapped extensional features. And there's a little histogram in the bottom right, which shows the orientation of those features clockwise from north. And the pie chart does it a little bit more visually. So mostly we're getting kind of east-west trending features. And in the upper panel, I've noted in the hashed lines the regions where we made these comparisons. So one is north of the equator, one is south of the equator. And what we find is that the orientations of those fractures don't change very much between north and south. Certainly not enough to have the mirrored kind of pattern that we would expect from tides. So the region that's below the equator, which is region A here, does kind of fit the predictions, but region B does not because it did not flip. Okay, so all of this to say that eccentricity driven tidal stresses are not a good fit for the fractures that we see on Sharon. What we think that means is that Sharon's orbit circularized, so lost its eccentricity before the ocean froze. And that in that case, when the ocean is freezing and adding a lot of extensional stress to the surface, there's no eccentricity stress to put on top of that pattern. Cooling stresses are isotropic, so they don't have a preferred orientation, but tidal stresses will have preferred orientations in different regions. So from this, we have a stratigraphy, or not a stratigraphy, but a chronology of there was an eccentric orbit and despinning and all of the crazy things that happened post Sharon forming impact. Those things happen very rapidly, and you end up with Sharon in a tidally locked circular orbit. You lose tidal heating, and then you begin to freeze out the ocean. And that's why these fractures do not carry any signature of tides. Next slide. We also see evidence of cryovolcanism on Sharon. So some of these features, again, are, well, actually, none of them look particularly like other icy bodies I've seen, but we do see these sort of lobate features and smooth areas and a lot of evidence that the surface has been modified. One of the tricky things about this activity is that it is also often attributed to an ocean. So the idea here is that as you're freezing out the ocean, you are pressurizing the ocean. Sorry, as you're freezing it out, you're adding thickness to the ice shell, which pressurizes the ocean. So if you're able to drive a fracture all the way through from the surface to the base of the ice shell, that ocean water is pressurized and will be ejected out of the fracture. This is the basic model for plumes on Enceladus and other icy bodies. The problem for Sharon is that in order to get a fracture to go all the way from the surface to the base of the ice shell, you actually need the ice shell to only be 10 kilometers or thinner. And that's just a function of the gravity and the overburden pressure of the ice shell. So Sharon, in the thermal orbital evolution models to date, usually has tons of kilometers, maybe 100 kilometers of ice. And there's just no way that we're going to be able to fracture through that with the freezing stresses that we currently know. So this is more like Europa case where you have a fairly shallow fracture compared to the thickness of the ice shell, as opposed to Enceladus where we think it cracked all the way through. So to be clear, I'm not ruling out ocean-driven cryovolcanism, simply pointing out that some things would have to change in our understanding. Either we would have to find reasons for Sharon to have melted much more than the current models suggest, or we would need to invoke some kind of ice shell plumbing system where you can inject water into the shell, or you can create um, in situ melt within the shell that then gets tapped by fractures. It's going to be very, very challenging um, to just bring ocean water directly to the surface through fractures from ice shell thickening. Next slide. So we see some cryovolcanic features, or at least they're hypothesized to be cryovolcanic on other icy bodies. And here are some nice images from Europa, Ariel, and Ceres. Uh, Again, these are all instances where you've brought material, liquid material or warm ice to the surface. And we have the same challenges in these bodies as we have on Sharon in some cases, right? So if you can't crack all the way through the ice shell, how do you get liquid onto the surface? Liquid likes to go down in ice and not up. Um, so this is still a challenge and a place where understanding how these things form on Sharon can really help us understand cryovolcanism and the sort of plumbing systems of all of these icy worlds. Next slide. I have no knowledge of the processes that are being depicted on this slide. Hopefully, Chloe would have known what to say here, but I will simply point out that there can be some significant sort of post emplacement processing of cryovolcanic materials depend like that are happening potentially on Sharon, but not on other bodies. And so uh, we may be able to do some things like dating and understanding, where these materials really came from by understanding how they might be later affected by surface processes. Next slide. Landslides and mass wasting are really interesting processes that, again, we see across the outer solar system on the icy moons. We don't always have great reasons to understand the origin of these processes, but we do see very similar processes. Um, she's pointed out here Miranda along Arden Corona. There may be some mass wasting in aerial smooth plains. Um, I haven't seen a lot of this on Europa, but certainly for the Saturnian moons as well. Next slide. And finally, impact craters, which we've heard a lot about this morning. Uh, there seem to be too few small craters, and that has mostly been attributed in the past to just a paucity of smaller KBOs. It's really interesting to think about Sharon, um, given what Kelsey presented earlier about Sharon potentially being, only 2 billion years old, and maybe we are losing a small number of them to resurfacing. So that's a very interesting new result. Um, the important thing that we take away from Sharon's impact craters is that uh, Sharon and Pluto indicate the same impactor population that we see in a few other parts of the solar system. And so what that tells us is that most of the outer solar system icy bodies are being impacted by the same set of things. So where we see deviations, such as at Triton or at the mid-sized icy moons of Saturn, we really have to think about what is causing those differences. It's not simply a change in distance from the sun, which was posited initially. So there are additional populations that must be affecting moons that deviate from this population. Next slide. So for Sharon, we have these two variable crater populations by region. So we have heavily cratered region in the north, which preserves the most complete impact rate. It's potentially older, and then we have these smoother cryovolcanic plains. And again, this tells us that there's been resurfacing on Sharon, and for some reason, it seems to be this polar dichotomy, which we see in other icy moons as well. Um, it's a bit too soon to speculate why or what the connection is. But on Enceladus, we have a polar dichotomy. We may see one on Miranda. and what I mean by this is that one pole seems to be much more geologically active than the other pole, and we don't really know why, because most of the processes we would invoke would be affecting both poles in a similar fashion. But this is again a place where, by looking across all of the icy moons, we might start to be able to pick out, what mechanisms would explain all of the moons simultaneously versus having to come up with a very different process for each of them. Um, and again, this last point that the moons have probably all experienced the same impact or flux, and so moons that do not have a consistent flux, consistent crater population, must be telling us that some other additional population affected the evolution of those moons. Next slide. So Chloe didn't include a conclusion slide, so I'm going to just wax philosophic for a few minutes and then open this up for discussion. Uh, so I think there's some really interesting puzzles with Sharon, because it's been difficult to connect the geology that we see in terms of fractures and canyons and extensional features, and then the cryovolcanism with a consistent internal evolution and orbital history. It seems like everything interesting happened early, and then Sharon froze, and we get everything that we see here. But if you want a source of cryovolcanism, that would suggest that either you had to keep Sharon warm later, or you had to have a way to bring material up through fractures, which again, we run out of processes very quickly to do these things. So I look forward to a discussion, and hopefully people in the audience have some ideas of directions we can go from here. Thank you.
Thank you very much, Alyssa. I don't any question. I mean, I might lead off with a just one question. I'm not sure if you. I don't think you mentioned it. Just the fact that Ariel, we also kind of see a bit similar to Vulcan Planitia, sort of what looks like material filling valleys that are sort of trough bounded. I don't know if you can maybe comment just on whether that throws any light on what might be happening at Vulcan Planitia, sort of maybe similarities in terms of the interiors of Ariel and Sharon.
I mean, I don't have a solution, but they're the same challenges as we go from moon to moon, which is that many of these mid-sized moons seem to have more recent geology or geologic activity than we would expect from our models. They seem to have higher heat flows than we expect from our models. So there's a problem that affects all of these. Um, and I'm still trying to hunt down what the solution is. But I would say Ariel is in that same category with Miranda and others. The difference with Ariel is that some of the models, like from Julie Castillo's paper, suggest that you could get a longer lived ocean in Ariel than in some of these other bodies. We just don't have the same sources for everybody.
Okay, thanks.
Hi, Alyssa. It's Paul Shank. Great presentation. Um, uh, want to go back to some of the things we were discussing earlier this afternoon about the origin of Vulcan Planitia and cryovolcanism and all that kind of stuff. And as it was originally presented in the 2018 topography paper, the crustal foundering model, which explains the moated mountains, the tilted blocks, and the the mighty slurps as one mechanism of foundering of the lithosphere, or probably the crust, because it may be a compositional thing, into the interior, and then you replace it with asthenosphere, I guess you might want to call it, something from down below, which is not a standard cryovolcanic mechanism. You don't have to worry about fracture, penetration through fractures and fissures and that kind of stuff. It's but so it solves a problem, but it opens up a whole bunch of other problems in how this whole mechanism actually works, because we've never seen it anywhere else before. So I wanted to see what your thoughts were on revising this question, reframing this question in a different way.
Yeah, Paul. So I think that you bring up a really good point. When I say, oh, I don't think that, ocean driven cryovolcanism works, it's only to point out that that one mechanism doesn't work, right? So this idea of foundering and sort of an upheaval of new material, we certainly didn't test that, and it seems like a viable mechanism. In the context of this talk, of course, my question is, why doesn't it happen other places, as you just said, right? So perhaps it's a compositional issue where you have the right mix of non-ice materials in order to create the right density contrasts or something like that that would help. So I would say we should kind of run with this idea of yours and think about how we can how we not modify it, but like what are the key components that would cause it to happen at Sharon and not others? That might provide us with some insights into how everything's working.
Right, and I remember talking with somebody at LPSC, and I can't remember what they said. I wish I could remember what it was, but there's some way, odd formation mechanism for the outer shell of Charon that was different because of the way the giant impact mechanism worked, and it resulted in a unique composition and density. Maybe it was you who mentioned it to me. I can't remember who it was, but it was like a trigger that was sort of like interesting. It's like, okay, you have a dense crust and you have a differentiated interior, and it creates an unstable situation. So it's like,
Yes, right. So something that I've been working on with a group um, through Habitable Worlds, the Habitable Worlds program, is trying to understand how large impacts affect the overall evolution of mid-sized moons. And so the idea is when you have a large impact, you disrupt whatever the initial evolution was going to be. And depending on, the interior structure at the time of the impact or the thermal conditions, maybe you get different outcomes in terms of broad evolutionary history than you otherwise would. So for that project, we had not gotten as far as looking at Kuiper belt objects or more complex chemistries. We were really focusing on generic satellites to get a sense of how much it matters. But I think there could certainly be something to look at there, where if we connected the newer impact simulations with inter evolution simulations, we might find something we were not expecting. Might help solve this problem.
Wait, before we go to Chris, those were all good thoughts, Alyssa. And yeah, I like the idea, the question Paul posed about, why is Sharon special? But Paul, I have a philosophical go back on the volcanism thing. What about, for examples of other examples, what about the Venus catastrophic resurfacing? I don't know if we all still believe in that anymore, but that was basically foundering of the crust, the original crust, and complete resurfacing. Would that be an analogous example? And if so, would you call that volcanism?
I suppose I'd have to go and read what they were actually proposing. I'm aware of the cratering history of Venus being, either catastrophic or an alternate, but I don't remember them actually discussing. So they did discuss a mechanism or different mechanisms to do the catastrophic resurfacing.
I'm also pulling these neurons out of the back of my brain that haven't been used in a while. So
that was,
you.
yeah.
But I was, and Bill's here, so maybe he can chime in. But
that was like decades ago when that discussion.
I remember it being described as sort of a foundering, yeah, and complete
yeah,
resurfacing in that way.
Yeah, I'm not sure if they went forward with those ideas very far, but yeah, it might be worth thinking about it as maybe
It does sound like
nice
catastrophic overturn for
Yeah.
Venus, right?
Yeah, there could be.
I don't know, just saying.
Be curious to see what the Venus people
You threw the
actually said.
challenge out there of, what could be considered analogous. So
For my dart in the wall, yeah.
Yeah. All right. Thank you.
All right. Hi, Alyssa. It's Chris Klein. Sorry. Nice talk. So, at the risk of wading into geology, I'm wondering if there are scenarios where the ice shell could have substantial thickness variations. And even if, let's say, the mean thickness is too thick, if there could be special regions that are thinner for reasons that you might elaborate on.
Sure. So that's actually a really easy question. Thanks, because we've been doing this exact investigation for Europa and Mimas recently. So tidal heating is location dependent. there will be some regions that have higher than average tidal heating, some lower than average. The poles in particular tend to be thinner if you just apply, a tidal heating model than other areas. But there are a few caveats to that. So the first is that the surface temperature has a large effect on how much tidal heating or how much heat you can pump through an ice shell, and therefore what is the thickness of that ice shell. So if you you have to map the surface temperature onto the tidal pattern in order to get a reasonable result for ice shell thickness. When we do that for Europa and for Mimas, we do see in the simplest models potentially very big differences in ice shell thickness. However, it's expected that a lot of those thickness variations will be muted by a heat transfer in the non-radial directions. So, basically you're going to be able to move heat to the left and to the right, not just up and down, which may smooth out those variations. It's also possible that you could have flow of the very ductile ice at the base of the shell. So everything that we're able to predict would be, the largest variations that you could ever get, right? And probably larger than what we would see in these bodies. But yes, you could get some thinner regions and some thicker regions, which maybe then would react differently. Something we have not done that I'm very interested in is looking at how thickness variations might respond differently to changes in the thermal budget. So if you have a very thick ice shell in one region because tidal heating is less effective there, and then you're freezing everything, does that thicker ice shell freeze more slowly and therefore have less stress? Or, does a thinner region thin more slowly because it has more tidal heating? That's not something that we've gotten to yet. But yes, you could have large variations in ice shell thickness, hypothetically.
This is just Paul again. I'll comment a little bit on that, in that Karen has some of the largest topographic amplitudes of a mid-sized IFC satellite, which does imply, or it implies some different variation in shell thickness. Question, of course, is whether those thickness variations drove some of the tectonics and geology we see, or are a result of those.